Okay, so let's get started. Welcome in this workshop. So I planned this workshop because I am very close to launching a new course. As you might know, I create AI courses that use C#. So it's a bit of a unique premise. I make AI courses where all the code assignments use C# and not Python. There's nothing wrong with Python, don't get me wrong, but I mean, as C# developers, it's kind of nice if we can use the same language for everything. You know, that we're not required to learn Python as well, and we have to constantly switch between C# and Python to build awesome applications, awesome business solutions with AI, with neural networks or complex machine learning algorithms. So my USP, the unique thing that I do is I create courses that will teach you machine learning and AI and computer vision, but I exclusively use C# for everything. So all the assignments are in C#, all the libraries, I use NuGet libraries for C# specifically, and all my applications are simple C# applications written in .NET Core. So it's pretty cool. I launched a course a while ago called Data Science with C# and ML.NET. And that course was for, it covered the ML.NET library, the Microsoft ML.NET library. It's an awesome library. It's a machine learning library. It's brand new. It's just a couple of months old. We're at version 1.1 right now. And I made a beautiful course around that. But now I am very close to launching another course, my second course, and that one is, that course is about building deep neural networks. Deep neural networks. So it's the Microsoft Cognitive Toolkit library. It's an awesome library. It's kind of like TensorFlow. You might know TensorFlow. TensorFlow is specifically for Python. And CNTK has the same feature set as TensorFlow, but it is specifically for C#. So it's a C# library. It's also a bit faster than TensorFlow. That's kind of cool. It's about when you create and train a neural network in CNTK, it's about twice as fast as if you would do the same thing in Python and in TensorFlow. So it's quite a cool library. So I created a new course around that library, around CNTK. So this new course is called Deep Learning with C# and CNTK. And so in this workshop, I'm going to show you a bit about the field of deep learning. I'm going to tell you a bit about deep learning. And I'm going to show you an app, a C# console application that I built that trains a convolutional neural network to recognize dogs and cats. So I've got this beautiful data set. I've got 2,000 dog pictures, and I've got 2,000 cat pictures. We're going to train a CNN, a convolutional neural network, to recognize the difference, to recognize a dog or a cat in an image. This is actually a very common challenge, but usually what people do is they just download a pre-trained neural network from the internet, a neural network that has already been trained on animals, and then you kind of tweak the network and you show it a couple of dogs and cats, and you kind of fine-tune it so that it recognizes dogs and cats. What I'm going to do is I'm going to build the whole thing from scratch. So I'll build the neural network layer by layer by layer from zero, and then I'll train from scratch on a data set with dogs and cats. I'll show you the whole process. So I think that's pretty cool. I'm going to quickly, I'm going to take a very quick break here and help a guy called Bob, who's trying to log in and who says that he cannot access the session. Let me just quickly, where is he? Yeah, it's right here. Hi, Bob, you have to click on the link in the email I sent you because it includes a password. There you go. So that should help him. Back to the presentation. There we go. All right, so that was a quick intermezzo. So hopefully Bob can join us too. So what do you think? Can you type something in the chat? What do you think? Is this, are you working with AI right now? Are you working with machine learning and neural networks? Do you want to learn about neural networks and machine learning? Like object detection with convolutional neural networks, is this something that interests you? Let's start with that. Type a yes in the chat if you're interested in object detection with convolutional neural networks. So I have a camera, I hook it up to a computer, I code some software, and I point the camera at something, and the computer says, ah, okay, that's a giraffe, that's an elephant, that's a car, that's a stop sign, etc. Is this something that interests you? Is this something that you could use in your work? What do you think? So type it in the chat. I'm just checking here if you guys are alive. Joanne, you're interested in it. Awesome. So that's Joanne. Anyone else? So Joanne, I've just established that you are conscious and you were watching this video. Very good. Dom. Yes, hi Dom. Bob. CNTK is an exciting approach. Indeed. Bruce, this is currently for personal interest. Okay, no problem with that, man. Personal projects are the best. Efson Nomini, very interesting topic, indeed. All right, so let's get started. So this whole workshop, hopefully it'll last no longer than an hour. Mohammed, you're interested? Nice. So hopefully this will last no more than an hour. I'm going to do a very quick intro, and then I'll show you the code. I'll run the code, so I'll train the neural network in a Visual Studio Code session, and I'll show you the training live. And then I've prepped a few screenshots of the fully trained neural network. Fully training the neural network takes about 5 minutes. I can just leave it running, and we'll see if it fits in this workshop. And if not, I've got a screenshot of what it looks like when it's fully trained. So let me show you some stuff. Quick aside before I start, if you have any questions about what I'm saying, what I'm telling you, just type it in the chat. So I've got this chat window open right there. So I can see it on my laptop. So if you have any questions, don't wait for the end. You can just type it right away, and I'll interrupt my story and I'll address your question. So let's get started. Oh my God, the presentation works. Okay, so let's get started. So like I said, I developed a new course. So I've got 2 courses now about machine learning in C#. So the first one is about data science, and it covers the ML.NET library. It's pretty cool. I mean, ML.NET can do all kinds of awesome stuff. It's mostly focused on data science. So we're talking about regression, classification, clustering, building ensembles, building decision trees, you know, these hardcore data science algorithms. It's a beautiful library, but it cannot train neural networks. That functionality is completely missing from ML.NET. You can, however, import pre-trained neural networks. So if you go on the internet and you find these neural networks that have been trained in Python, then you can download these configuration files and you can load them into an ML.NET pipeline, and you can run these fully trained neural networks. But what you cannot do is train these neural networks from scratch. So it's quite a big limitation, actually. ML.NET it's more like a toolbox that lets you achieve very well-defined tasks. So it's a task-oriented API for machine learning. And it's completely unlike something like TensorFlow, which is a tensor library that lets you build a neural network layer by layer and node by node. You start from 0 and you stack the whole thing layer by layer. So if you want to do that, if you want to custom build your own neural networks and train them from scratch on your own system, then you're going to need a tensor library. Now, TensorFlow is a famous example. You can actually call TensorFlow from C#, but it's really difficult. And the reason is that the API, the TensorFlow API, has been specifically designed for Python. And Python it's not quite like C#. The Python interface, it gets very messy if you want to tap into a Python interface with C# code. So the beauty of CNTK, the cognitive toolkit, is that it does the same as TensorFlow. So again, it's a tensor library, but it has an API that has been optimized for C#. So it has a very clean API. You can tap into CNTK with C# code. CNTK is a NuGet package. So with a single line, you can add one single package to your application, and then you have the full neural network training engine linked into your app. And you can easily tap into the API. So it's a lot easier to program against CNTK than to program against TensorFlow. Plus, you don't need the Python runtime, which is also a big plus if you're deploying your applications in an enterprise environment. CNTK is just a bunch of DLLs. So it's written in C++. It has a bunch of advantages if you have like pre-existing C# software, like enterprise software, and you just want to drop in AI modules. You want to do little machine learning experiments and just drop them into an enterprise solution. Then CNTK is a better solution than if you try to somehow jump into this TensorFlow domain, you know, and call into Python code. So I like the library a lot, and I built this course around it. Now I'm about 2 weeks away from launching this course. It's called Deep Learning with C# and CNTK. Next Monday, I'm going to open up the course. So if you go to the website, you can actually sign in. There will be a link, there'll be a button where you can buy the course, and the whole thing opens. So we're 1 week away from launch. So remember that URL at the bottom of the screen. You have to go to that page 1 week from now, and you'll see a link that will take you to this course, and then you can sign up if you like. So I'll send you a reminder in a week that the course is live, and you can take a look. But today I'm going to give you a sneak peek of what's in that course, and you know what's in the CNTK library, and how you can do deep learning in C#. So if you look at all the libraries that Microsoft has to offer around AI, it's quite a lot actually, and it's cool stuff. I'll start in the top left. So we got the Azure Machine Learning Service, Azure Machine Learning. That's an Azure service, and it lets you build neural networks in Azure, in the cloud, at scale. So it's really nice if you want to build these huge neural networks that are way too big to train locally. Next one is Cognitive Services, or CNTK. Cognitive Services is a bunch of APIs for specific tasks in the cloud. These tasks are stuff like speech recognition. If you want to do speech recognition, then you can tap into the Cognitive Services, and you can upload a sound file, and you can pull back down the English transcribed text, you know, the spoken words. So you can do speech synthesis, difficult word. You can do speech recognition. You can build bots with the Cognitive Service. You can do object detection. You can do face recognition. So it's a whole bunch of pre-built APIs for these specific tasks. Then the bot framework, I mentioned it already. You can build your own conversational bots. Top right, ML.NET, Microsoft's new machine learning library. Really nice library, task-oriented, lets you do really powerful stuff, but it cannot train neural networks from scratch. If you want to do that, you need to use the Cognitive Toolkit, CNTK, which I will cover in this workshop. And finally, you've got Azure ML Studio. And that's a really nice, it's a graphical environment that lets you build, design, train, and run neural networks without having to write any code. So it's purely visual. So it's like this visual design canvas where you can just connect components together, and you're building a neural network that way. So it's Microsoft's attempt to make building neural networks a visual experience. It's actually quite nice. But let's talk CNTK. So CNTK is a really cool, library. I'm constantly moving my chat window around on the screen so I can actually read what it says. So CNTK is a really nice library. It's a toolkit that lets you build neural networks and train them and run them. And so it was created by the Microsoft Speech division when they were working on speech recognition neural networks. Was created in 2012, so quite some time ago, and it's open source. So in 2016, they put it on GitHub, and it has an MIT license. So that's really cool. So you can fork the Cognitive Toolkit It has a few bugs. You can actually debug it and then use your own branch of the library. So it's completely open source. You can check out the complete source code. So it's already been forked more than 4,400 times. And it's got like 16,000 stars on GitHub. So it's very, very popular. And the code has been contributed to by more than 140 people from all kinds of famous universities like MIT and Stanford, and awesome companies like NVIDIA and Intel. So there are some real powerhouses, some real strong companies and people behind this library. So this definitely isn't a toy. It's a very powerful tech. So CNTK allows you to create, I see a question. So Zandomini, F. Zandomini, you got a question. Sorry about the simple question. Hey, there are no simple questions, man. Can you briefly mention what is a neural network? What would be a good analogy in a production business environment? Well, check this slide. So a neural network is a specific type of machine learning algorithm. It's a specific algorithm. And it is basically a similar of biological neural tissue. So if you look at human brains or animal brains, if you look at how they function, they consist of billions of neurons that are interconnected. So they're neurons and they're connected with other neurons. So it's this whole graph of neurons that communicate with each other. And they behave in a certain way, and biologists have kind of figured out how neurons work by experimenting with them. And we simulate that in a computer. So what we do is we simulate neurons. So in this diagram, the circles are the neurons, and we simulate the interconnections between the neurons. That's those lines that you see. And the neural architectures that we see in nature, we're basically just copying them into a computer and see how they work. So for example, at the bottom left, you see a specific neural architecture called a convolutional network, a deep convolutional network. And you see it's this kind of a funnel shape. It starts with yellow nodes, and you got these purple convolution nodes, and they funnel into a point, and then there's these green layers at the end. So get this convolutional neural network is literally how our retinas and our optic nerves work. So that's basically reverse engineering the biological tissue that's in humans, and simulating them in a computer. And it turns out that these neural networks are extremely well suited to recognizing patterns. They're really good pattern recognizing engines. You can train these networks on data, and they will start to recognize patterns in data. They can make specific predictions based on those patterns. So you can train these algorithms to do a lot of stuff. Like, for example, I could show a picture to a neural network, and the neural network could then say, I recognize a cat in this network. So the network actually recognizes what a cat looks like. It learns what a cat looks like. So in a business environment, you can do all kinds of cool stuff. You could show a customer profile to a neural network and ask it to predict how much money this customer will spend with your company. So what the total lifetime value of this customer would be for your company. What you could do is you could show the revenue of the last 12 months to your neural network and ask it to predict what the next 12 months will look like. So what it's going to do, the neural network is going to predict next year how much money you're going to make, how much money your company is going to make. And the way it does that is it looks for patterns in the historical data, and when it finds these cyclical patterns, it just extrapolates them forward, and it predicts the future that way. But if you show a picture to a neural network, then it will start recognizing specific stuff like cat ears, these triangular cat ears. It will recognize that, and after a while, it will learn that if I show it an animal, and there are two cat ears, and there's fur, and there's a specific color, then the neural network will learn to conclude that that's going to be a cat. So you can train them to do anything. You can train them to recognize speech. So I could play an audio file into a neural network, and on the output side, I could get English text. So there's all kinds of cool stuff that they can do. I mean, they are simulations of biological neural tissue. So anything we can do, a neural network can do too. The only boundary conditions, the only constraints on this is you need to have the correct neural architecture. So you can see these are different kinds of neural architectures that you can design, and specific architectures are suited for specific tasks. So this convolutional network in the bottom left is very, very, very good at recognizing objects in images. So it's a visual pattern recognition engine. So it can recognize traffic signs and cars and people and animals and objects and all kinds of stuff. So whenever we build object detectors, we always use this convolutional architecture. Now, a speech recognition network looks differently. It has a different setup. When we're looking for, when we're trying to classify information, so if we have like 1,000 inputs and we need to translate that into 3 or 4 or 5 discrete output classes, then we use something called a feed-forward network. You can see it in the top row, the second one from the left, feed-forward. So that's a specific kind of network that we use to condense a lot of input data into only a few discrete outputs. Okay, question from Don. Can a neural network convert language with speech recognition? Let's say a hearing aid will convert Spanish spoken words to English language. Yes, yes, absolutely, that is possible. I have to say though, the neural network, the size of the neural network that you need to do this reliably is gigantic. You need an enormously large neural network with billions and billions of nodes and interconnections that need to be trained. Training a neural network of this size takes months, and you need terabytes of audio data, to reliably train the neural network. So only large companies can do this, like for example, Microsoft, who just added this capability to Skype. Believe it or not, you can literally do this in Skype. If I Skype someone, for example, if I Skype a Spanish person and that person speaks Spanish to me, I would hear it as English because Skype can do live translation. And then when I speak English, the other person would hear that as Spanish. So Skype can already do translation on the fly. And it literally works with neural networks. Microsoft has a very large neural network hosted in Azure that does this. So yeah, Dom, great example. You can definitely do that. And so these APIs are slowly becoming available. This is where these cognitive services come into play. Every time when Microsoft builds these large neural networks and they get them to work reliably, they open up the API as part of their cognitive services. So speech recognition is already in the cognitive services. Translation is already in there as text translation. And the next step would be to take audio files and literally translate them into someone speaking that same text in a different language. And I'm sure it's only a matter of time before Microsoft opens up that API. So yeah, really cool stuff. So these are a bunch of neural architectures that you can build with CNTK. And so you build these networks layer by layer. So these vertical slices that you see in these images, we call that a neural network layer. And the leftmost slice is the input, and on the right-hand side, that's the output. And everything in between, we call those hidden layers. So we build neural networks like sandwiches. We stack slices on top of each other. And if we need a complex neural network, we have lots and lots of slices. And if we have a simple neural network, we only have 2 or 3 slices. So here, the sandwich is like this, right? And in this diagram, you have to kind of rotate it 90 degrees. The slices are stacked like that. So pretty clear, right? So this is the neural network that I'm going to build in this workshop. So it's a really cool convolution network. So it has a bunch of layers. So you can see I sort of stack the layers in a 3D image. The input side is at the top left. So that first green slab that you see, that will receive the input. And the input, of course, is a picture. I'm going to hold up a picture of a dog or a cat to my neural network. And the neural network needs to tell me that's a dog, that's a cat. So that green layer will receive all the pixel data of the image. So every individual pixel goes into a specific node in the neural network. So I have 150 by 150 pixels in my images. So my images are 150 by 150. So that green input layer of the neural network is also 150 by 150 nodes. So every individual pixel can go into a node. And then I do this really cool process called convolution. If you want to learn what convolution actually is, that's a very long subject. You have to join the course for that. I'll explain in detail what convolution is and how it works in the course. But for now, just, accept that it is a magical mathematical algorithm that can recognize patterns in images. So convolution is that green layer. So that's a convolution layer in my neural network. And then the next layer is called a pooling layer. So the pooling layer is in there because it's a really cool feature. Pooling reduces the size of the output. So pooling makes the output smaller, but it doesn't lose any information. So you can view a pooling layer as a form of lossless compression. The image is being compressed, so it's getting smaller. It's no longer 150 by 150. It's like 130 by 130 or 100 by 100. So it's getting smaller and smaller. But all the information is still in there. So all the details of the image is still in that smaller image. Nothing is getting lost. So it's really weird that you can actually compress an image and not lose any detail, but that's what this pooling layer does. So it's a magical mathematical operation. Now we do that because training a convolutional neural network without shrinking the output would take way too long. If I would just stack 6 convolution layers on top of each other, and I don't make them progressively smaller, then I would have so many trainable parameters that it would take weeks or months to train the whole thing. So that takes way too long. So with the pooling layers, I speed up my training without losing accuracy, without making my neural network less accurate. So it's a really cool trick. So the orange pooling layers reduce the output, and then the next convolution layer, you can see that the convolution layers are getting smaller and smaller and smaller. So we get this cone shape. I remember the cone shape, that was right here, bottom left. You can see that those purple nodes going like that. That's what you see here. It's these layers getting smaller and smaller. Now at the end, you can see there's a dropout layer. There's a red slice, a red neural network layer. Dropouts, it's a special layer that we use to stabilize training. It's kind of weird, but if we don't put that dropout layer in, then the neural network will often crash during training. It will hang during training, and it will no longer learn new things. So you could basically visualize that as that the neural network gets stuck in an infinite loop, and no matter how many new pictures of dogs and cats I show it, it just refuses to learn any new information. So the dropout layer helps training. It guarantees that the neural network will continue training for as long as I show it new pictures. Now, way at the end, we've got a dense layer. What the dense layer does is it prepares the output. So it takes this compressed pattern information and it translates that into what's going to become a dog and a cat output. So at the very output side of the neural network, I will only have 2 nodes, 1 node for dog and 1 node for cat. So if I hold an image of a dog in front of the neural network, the dog node at the output side will light up. It will activate. And if I show a cat, then the cat node will activate. But if I go 1 layer into the neural network, so I'm not at the output layer, I'm going 1 layer deeper, then I don't have these 2 outputs, I have like 50 outputs or 100, for example. And these outputs represent things that the neural network recognized in the image. For example, cat ears, or a cat nose, or whiskers, for example. The neural network has identified whiskers in an image. So that's got to be a cat, right? Because dogs don't have whiskers. Another thing could be the neural network has identified a really large black nose. That's probably a dog, because cats have small noses and they're covered in fur. So if I go 1 layer deeper, so I'm talking about this large, dense blue layer that's almost at the right hand, at the output side of the neural network. At that point in my neural network, I have 50 or 100 different nodes, and they all represent different features that have been detected in the image. And we're talking about ears, we're talking about noses, we're talking about paws, we're talking about a tail, we're talking about a fur, we're talking about colors, patterns in fur, so all kinds of interesting visual patterns that the neural network has discovered. So what these dense layers do is they take these features and they condense them into only 2 outputs, dog and cat. So a dense layer is specialized in doing this combination work, where it says, okay, triangular ears and a tiny nose and a calico fur pattern is a cat. If I see this and this and this and this, that means it's a cat. those kinds of decisions, these blue dense layers are really good at doing that. So that's why in these visual neural networks, we always have these blue dense layers at the end to make sense of all the individual features that have been recognized in the image and condense that back into a few discrete outputs. So in my neural network, I'll have 150 by 150 inputs, one for every pixel. And on the output side, I have only 2 nodes, one for dog and one for cat. So this is what I'm hoping for. You know, I've got this picture of a cat. I show it to the neural network, and then the neural network needs to tell me, yep, that's a cat, you know. So it could also trigger on eyes, you know, like cat eyes with the vertical slit. The neural network will learn that those, you know, those are cat eyes and that dog eyes are round. So it can look at eyes and use that as a hint to, you know, learn if it's a dog or a cat. So let's get to work. I will show you the code. Any questions so far about this background, about neural networks? I'm going to switch to my coding environment, but if you have any questions, put them in the chat. That's the code. Where's my terminal? Here's my terminal. No, I'll show you the dataset first. It's going to be fun. Check this out. So I've got 2,000 images. This is a famous dataset, the dogs and cats dataset. This was a challenge, a Kaggle challenge, where you had to build a neural network or any kind of machine learning algorithm that could, you know, recognize dogs and cats. Now, if you look at these images, all kinds of different sizes, all kinds of different orientations. I mean, look at image number 6. You know, that's not a cat, that's a woman in bed with half of a cat head sticking out of the blankets. So this is very messy data. It's not just the cat centered on screen every time, viewed from the same angle every time. This is like one big bag of cat images, you know, and some images, some cats are really hard to recognize. We got like image 26, we have a woman kissing a cat. Image 45, you can see there's a blanket in the picture. So very messy data. So, you know, just to show you that the convolutional neural network has quite a challenge here. You know, there's a lot of visual noise in these images. I'll show you the dogs as well, right here. So here are the dogs. So again, all kinds of orientations. We have portrait images, landscape images. We have dogs outside, the dogs inside. We have all kinds of different colors. We've got, sometimes the dog is facing away from the camera, sometimes the dog is looking at the camera. We have angry dogs, happy dogs. So it's one big mess, basically. So this is a really nice data set to train on, because it's a challenge for the neural network, you know. We humans, we can see the difference between dogs and cats. Could we train a machine to do this at the same level of accuracy as we can do? So let's give that a try. So here's the PowerShell environment. So I've got this terminal open. This is PowerShell, and I've got my project right here. And this is, oops. This is a basic .NET console application. So I'm using .NET Core version 3. Let's see if I can type that. .NET list SDKs. So you can see I'm using the 3.0.100 SDK of .NET Core. So it's basically just .NET Core 3. And yeah, I mean, that's it. I'm moving windows again so I can see what I'm typing. And I've created this project like this. So just .NET new console -o cats and dogs. I won't press enter, but this is what I typed this morning to create this project. So it's a completely normal console application. There's nothing special about it. Just .NET Core 3.0 console. Now, if you look at the project file, sorry, my mistake. If you look at the project file, you can see the packages that I imported. So the interesting package is cntk.gpu. So CNTK.gpu is CNTK, and it's the version that uses my GPU. So this computer right here, this is a Service Book 2, and it has an NVIDIA 1060 processor built in, which is awesome because that means the CNTK library can train using the GPU, and that speeds up matters enormously. This code will work on a CPU, but then all the tensor operations are being done by the CPU, and it's a lot slower. So with GPU, you get maximum performance, and it's really quite fast, actually. So I'm using CNTK.gpu. I'm using xplot.plotly. That's a plotting library from F#. It's a really nice library. It's ideal for making little plots at the end of a console application. So I'll use it to create a graph at the end. And I'm pulling in f#.core because xplot is an F# library. So I need the F# core runtime library to be able to run it. So you can do that. You can pull in F# code into a C# project. You just need to add that core library, and then everything will work. So this is the environment. It's a simple console application, and here is the code. Moving my window again. Here we go. So I'm going to show you the entire code. So what I'm doing is I've created mapping files that tell the neural network where to find the cat and dog images. So the mapping files look like this. So you can see it's one long list of cats and dog images. And I've got two columns. I have the file name. And you can see it's a dog or a cat. It's alternating, dog, cat, dog, cat, dog, cat. And there is label in the second column. So the second column is a number, and 1 means it's a dog, and 0 means it's a cat. So this is my training data. I'm going to feed this file into the neural network with some code modifications, with some code to massage the data. So basically, I'm going to show these images to the neural network, and I am going to tell it what the animal is. Is it a dog or is it a cat? And I'll train the neural network that way. And the neural network will then, during training, it will constantly reconfigure itself, and it will try to create predictions that match the labels that I provide. So I'm going to show it a dog and tell it this is a dog, and then the neural network will make a prediction. And if it predicts cat, then that's obviously wrong because I'm telling it's a dog. So then the neural network will reconfigure itself to try and create a dog prediction in that specific situation, in that specific case. So I'm constantly showing images to the neural network and allowing the neural network to optimize itself to get its own predictions as close as possible to these labels in this file. So that's a training file. So this is what the code looks like. So you can see that I'm creating some file paths here. I'm just combining the current directory with the file name, train map and test map. So I have a file for training and a file for testing. I'll get to that in a second. Got some constants here. You can see my images are 150 by 150 pixels, and I've got 3 color channels. So I'm showing color images to the neural network. And then here, look, I'm going to train on 1,600 images. So I've got 2,000 images, and I'm going to use 1,600 of them for training. So I'm continuously going to show these images to the neural network and ask it to create predictions that match the real answers as closely as possible. And then I'm going to keep these 400 images, I'll set them aside. And what I'm going to do is, after I've trained the neural network, I'm going to show these 400 images to the trained neural network. I'm going to ask it to make these predictions. And I will calculate the total amount of mistakes that the neural network makes in both situations, so during training and during testing. And I'll get to that in a second, why I'm doing that. So I'm going to train on 80% of all images, and then I'm going to test my trained network on 20% of all images. So let's start. First thing I need to do is set up 2 readers. So these are image readers that will load the images, convert them into pixel data, convert them into an array of floats, basically, and present them to the neural network. So the cool thing is I've got this beautiful class called an image reader, and I can just instantiate it with these get image reader calls. and point it to the right file. You can see that the file names are here. See here, test map path and train map path. And so these readers will basically, they're responsible for loading the images into memory and presenting them to the neural network. Next thing I need to do, I need to tell the neural network how many inputs there are and how many outputs there are. So remember, I have 150 by 150 pixels on the input side, and I've got dog and cat on the output side. So on the input side, I've got image height by image width, right? 150 by 150, but I also have 3 color channels. I have the red, the green, and the blue pixel components that I need to input into the neural network. So this is actually a 3-dimensional array that I'm feeding in. 150 by 150 by 3. So the full color image goes into the neural network as a 3-dimensional array of float values. And on the output side, I have 2 floats. So one will be the probability that the image contains a dog, and the other number will be the probability that the image contains a cat. So 2 probabilities. Then I will build the network. That's what this code does. So you can see I'm building this network layer by layer. And the first thing I do is I take all these pixel values and I divide them by 255 because I want numbers between 0 and 1. The pixel color components are between 0 and 255. And neural networks just work better if the input is a number between 0 and 1. So I just divide everything by 255. And then here we go. Convolution layer, pooling layer, convolution layer, pooling layer, convolution layer, pooling layer, convolution layer, pooling layer, the famous dropout layer to prevent the training from hanging, then a dense layer to take these features that have been recognized in the image and combine them. You can see there are 512 features, discrete features, that have been identified in the image. And here I combine them into 2 outputs. So on the output side, I've got only have 2 nodes, one for dog and one for cat. And this is the whole neural network. So this is how easy it is in CNTK to build a neural network. You just build it layer by layer by layer. Super easy. Then I set up 2 functions. I need to determine how I'm going to train my network. How am I going to measure how good the predictions of my neural network are? I can use different functions for that. And the standard function for this kind of machine learning problem is called cross entropy with softmax. It's a standard mathematical algorithm for measuring the mistake that the neural network makes. So how far off its predictions are. So I'm going to use that to train the neural network. And I'm going to use a different function called classification error to report on the console while the network is training. Classification error is very simple. It's the number of mistakes that the neural network makes, expressed as a number between 0 and 1. 0 means no mistakes at all, and 1 means that every prediction the network makes is wrong. So I show it a dog, it says cat. I show it a cat, it says dog. You know, it's wrong every time. That's an error of 1. So we want the classification error to be as close to 0 as possible, or preferably 0. Okay, then I'm going to set up a learning algorithm. This is a mathematical algorithm that's going to train the neural network. And I'm going to use something called an Adam learner, which is a very popular learning algorithm for training neural networks. It's a nice general purpose algorithm that works in many cases. So I'm going to just set that up. These parameters are just defaults. These defaults work really well. If you do my course, you'll notice that these numbers show up in every assignment. This is just default values for the Adam learner that work in pretty much every scenario. So I just reuse them every time. Then I set up a trainer and an evaluator to train the network and to test the network. And then we start training. So I am going to train my neural network for max epochs. So the number is right here. I'm going to train my neural network for 100 epochs. So we're going to train it 100 times, basically. And during the training, here's what I'm doing. I'm going to extract a batch of images. Now the batch size is right here. Batch size is 32. So that means during training, I show 32 images to the neural network in one go. 32 images. The reason I'm doing that is it speeds up training. The higher the batch size, the faster I train the network, but the lower quality predictions I get. So this is a trade-off. If I make this number really large, like 10,000, then I have super fast training, but the predictions are not going to be great. If I set the batch size to 1, then I'll have the highest quality predictions, but training will take forever. So 32 is kind of a sweet spot for 2,000 images. It's reasonably fast on my system. So I grab this batch, I split the batch into a feature batch, that's just a collection of 32 images, and a label batch, that's the 32 answers. So dog, cat, 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 dog, you know, just a list of answers. And then I train the neural network on these two batches. So I show it 32 images, I give it the 32 answers, and I ask the neural network to reconfigure itself so that its own predictions will more accurately match those labels. And then at the output side here, after training, I get the loss, the cross entropy. It's a measure for how good the predictions are. And I get the training error, so the total number of mistakes that it made. And I just add them up. And at the end of the loop, I divide the total number of errors by the number of times I went through the loop. So then what that gives me is the error expressed as a number between 0 and 1. And I show that on the console. I write that to the console. Next, I take this partially trained neural network. So remember, we're inside a for loop, and this is just the first loop iteration. So I take this partially trained neural network, and I'm going to test it. So again, I grab batches, but now you can see that I'm using the testing reader here. If I scroll up, you can see this is the training reader. So this is this set of 1,600 images. And now I'm using the testing reader, which reads the set of 400 images. So I'm going to test on these 400 images. I'm going to test the neural network on this batch, and that gives me a testing error. So this is the number of mistakes that the neural network makes on this test batch of 400 images. And then I loop, you know, I keep repeating this for all the batches. I divide by the number of batches at the end, right here, and I show this on the console. So what this does is it calculates the error, the total number of mistakes during training on the 1,600 training images, and then it shows me the total number of mistakes made for the 400 test images. And the reason I'm doing this is because if I train on images, eventually my error will be 0. If I train long enough, the neural network will perfectly predict every single image. However, if then I take a completely new picture of a dog or a cat and I show it to the neural network, it will do a terrible job. It will have a really bad prediction accuracy. And we have a special name for that. We call this overfitting. And is when the neural network has perfectly trained on our training data, and it has become such an expert on that specific training data that it really sucks at general data, you know, when I show it new data. So it's called overfitting, and an easy way to detect overfitting is by continuously testing the neural network on these images set aside. These 400 images that I set aside, I'm just continuously going to test the neural network on those images. And then I can detect from the results, by comparing those two error values, I can very easily detect overfitting. And I'll show it to you when I run this up. You'll see what overfitting looks like. So that's the end of the for loop. So then my neural network is trained. And then finally, I use XPlot to plot the, the training error and the testing error. So what you're going to see is the number of mistakes that the neural network makes during training and during testing for every training epoch. We have 100 epochs, so you'll see a plot of 100 X values, and then you see the errors on the Y value. But look at this select. I actually plot 1 minus the number of errors. So that gives me the accuracy. And accuracy it's a nice number. An accuracy of 1 means the predictions are perfect. Every prediction is spot on, is correct. And an accuracy of 0 means that every single prediction is wrong. And random chance would be an accuracy of 0.5. Then the neural network is correct half of the time. So the plot is actually going to show accuracy. And here at the end, I take this plot and I save it to disk in an HTML file. All right, gonna run this app. Check this out. So let me go to PowerShell. I'll compile the app like this. So I'm compiling this app. It's just a .NET Core 3.0 app. And note the P flag. I'm compiling for the x64 platform, so 64-bit Intel. I need to do that because CNTK will only run in 64-bit mode. It cannot run in 32-bit mode. So I have to force the platform to 64 bits. So that's it, it works. Now .NET run. There we go. So now my app is starting up. Here you can see the neural network. So look at this number here. This neural network has 3,453,000 trainable parameters. So during each training epoch, and during each batch training, these 3.5 million parameters are being optimized to create reliable dog and cat predictions. Now here's the first training epoch. You can see the training error is 0.490, so that's only slightly better than random chance. And my test error is 0.5. So that's literally like I'm throwing a dice, you know? It's like a random number generator. But now, as we are training the neural network, you can see that the training error is dropping quickly. So it's at, we're at 0.293 already. And the testing error is at 0.352. So we're already much better than random chance. So this is the number of mistakes that the neural network is making while trying to predict dogs and cats. So we got 6 epochs already. So you can see it's quite fast actually. I'm training 3.5 million parameters. I'm optimizing them. I'm showing 2,000 dog images and 2,000 cat images to the neural network. So I'm showing 4,000 images. Each image is 150 times 150 times 3 bytes in size. And I am optimizing a neural network by tweaking 3.5 million parameters to try and optimize these outputs to get reliable dog and cat predictions. So it's a lot of work happening behind the scenes here. And yet, a single epoch takes about 10 seconds. So you really see the power of the GPU here. This is my NVIDIA 1060 GPU being put to good work. And yeah, you can see it's slowly dropping, right? So we're at 0.192 already. So that means for 100 images, the network makes 192 mistakes. Sorry, for 1,000 images, it makes 192 mistakes. So it's pretty good, actually. So 0.188. Or you could say 18 mistakes for 100 images. Is that correct? 1.8. No, it's incorrect, actually. It's times 100. Huh? So it's 0.176, 0.64. So you can see the training error is dropping nicely. It's getting lower and lower. The testing error is also dropping. And the network is getting better and better at recognizing dogs and cats. Okay, so a question from Fabian. Mark, here's another simple question. Why are we talking about GPU and not CPU? So the GPU is very well suited for calculating neural networks, for training neural networks. What we're doing here is linear algebra at an absolutely massive scale. So we're doing matrix multiplication with 3.5 million floating point numbers. And the GPU is just designed for that stuff. So the built-in operations in the GPU are just perfect for running and training neural networks. So we preferably use the GPU. Now, if there is no GPU, or there is no NVIDIA GPU, then the library will default to the CPU, but the CPU doesn't have these fantastic matrix multiplication instructions that we can use. So the code will have to use a loop to use more simple multiplication to, eventually multiply these large matrices. So the CPU, it will work, but it's slower. So we always prefer a GPU when training neural networks, and we prefer a really fast GPU. So like the most overpowered NVIDIA GPU that we can find. So the 1060 is not the fastest GPU on the market. It's a mid-range NVIDIA processor. But I mean, it's pretty nice to have it in a laptop. And you can see that it's not bad, actually. It really speeds up these calculations. If I run this on a CPU, it takes about 50 seconds for every single epoch. And you can see with the GPU, it's 10 seconds, or maybe 1, 2, 3, 4, 5, 6 seconds, 6.5 maybe. So that's quite fast, actually. So we're using, we're always using graphics hardware for these. Yes, like you say, Fabian, we're always using graphics hardware for these heavy calculations. Correct. So any other questions? I mean, this is running, so might as well do a little Q&A while we wait for the results. I have 100 epochs. I'm going to let it finish so you can see that the whole thing is live. I actually made a screenshot of the finished training, but I think it's more fun to just let this thing complete, and then I'll show you the graph. So there's a massive amount of calculations going on in the background now. And okay, so Bruce, I assume that GPUs are much better for floating point operations as opposed to integer usage. Yes, exactly. And neural networks, every node is a floating point number, a float. So it's a short, a single type. And every interconnection between nodes, so all the lines in the neural network diagram, it's also a float. It's a floating point number. So all these numbers need to be tweaked, and the training algorithm uses large matrix multiplication to train the neural network. So, I mean, we want GPUs here because we have these massive floating point matrices, and we multiply them with other massive matrices, and we want to do that as quickly as possible. Harvey question, will the video recording be available to be sent on our emails, or will it be on YouTube? You'll get an email tomorrow, and it will contain a link to YouTube. So watch your inbox tomorrow, and you'll get the recording. I'm recording this as we speak, so all good. Bob, with other applications that we have done, we have seen that a high-end CPU takes approximately 10 times as long. Yeah, I'm seeing the same scaling on my laptop. This takes about 60 to 70 seconds per epoch on the CPU, and 6 to 7 seconds right now on the GPU. So a factor 10 speed up using a GPU. So, I mean, you need a GPU if you want to get serious about machine learning, about training neural networks. If you don't have a GPU, you can actually do this. The first version of this course, I actually created that on a MacBook Pro, which has an Intel GPU, which is totally hopeless because the driver is unsuitable for machine learning, for training. So I had to do everything with my CPU. So the whole thing with training took 2.5 hours. So it took a bit longer than what we're doing right now. But still, I managed to build a whole course with that under-dimensioned hardware. So you can actually get by with a CPU. If you have a MacBook, a modern MacBook Pro, then you can't use the GPU, but you could run this code in theory. It would just take much longer. Fabian, is it simple to force an algorithm to use GPU instead of CPU? Yes. So my code picks the fastest device on the computer and uses that to train the neural network, but you can easily force it to use CPU instead. So it's in CNTK, it's called a device descriptor. You get this array of devices, compute devices on your computer, and one will be the GPU, one will be the CPU, and then you can tell it, use that device. So you can force it to GPU or to CPU if you want that. Bob, the GPU is better at parallelization of the matrix operations. Even a standard FPU does not do massive parallelization. Correct. And we're doing thousands of matrix operations here, and the matrices have millions of elements. So any kind of parallelization, you know, breaking that out and running it in parallel is welcome here. We want the maximum performance. So we got epoch 58 already, so it's going nicely. You can see that my error is at 0.049, which is pretty awesome. So I think that means only 49 mistakes out of every 1,000 images, which is very nice. Now look at the testing error. So the training error is at 0.57 now, and the testing error is at 0.236. So they're starting to diverge. So this is what I meant by keeping those images separate in this separate testing testing pool to test the network on. You can see that this neural network is getting really good at predicting the training sets. So it's becoming an expert at the training data, but it's losing sight of what dogs and cats look like in general. So what it's probably doing is like every image outside, you know, in grass, outside in the grass, has a dog on it. Because, you know, when we walk a dog, the dog is not always on a leash, right? We go into the park, we take the leash off and the dog can run free. Now, if you try that with a cat, you take a cat into the park and you take the cat off the leash, then whoop, the cat is gone and you'll never see it again. So pictures of cats are always indoors. Pictures of dogs are sometimes inside and sometimes outside. So this neural network could start concluding, like, when I see grass, like this green surface, then it's a dog. And I mean, there's nothing in the training set that disproves it, right? So the neural network can come to these false conclusions based on certain patterns in the training data. And when I show it data, you know, other data, new data, then we would see that the neural network has learned all these incorrect conclusions, all this incorrect knowledge, and it generates incorrect predictions. So that's why I have this testing set. I have these 400 images set aside to keep the neural network honest. You know, it might learn weird stuff, but so I show it those 400 images that I keep aside to constantly test if the neural network is really good at general purpose dog and cat detection. Okay, Fabian, I have to go now. Have a great day, everyone. Fabian from the Pacific Coast in Canada. Fabian, thanks for joining. You can watch the rest in the recording. Harvey, can we have a sample later where we will have an image that has both a dog and a cat on it? I haven't got that in this workshop, but you can definitely do that. Remember, you have two outputs on the neural network side. So it gives you the probability that there is a dog and the probability that there is a cat. So two separate values. So if there is a dog and a cat in the image, then both these outputs can get activated at the same time. You would probably see, you know, like 49% dog and 51% cat. And then, you know, the image has both. So yeah, you can have that. So we're at epoch 79. We have to go all the way up to 99. So we're almost done. Harvey, one point there. When designing neural networks, we always have to decide if we want mutually exclusive outputs or outputs that can be active at the same time. So in this case, my outputs are mutually exclusive. It means that if I show a picture of a dog and a cat at the same time, a dog and a cat in the picture, then the network will pick one of the two. It's going to say it's either a dog or a cat. It's going to make a choice. However, I could redesign this neural network so that it is able to identify a dog and a cat in the same image. I need a slightly different configuration on the output side of the neural network. So yes, it is possible, but this specific code has been configured to generate exclusive outputs. So that's a decision you have to make up front. Do you want mutually exclusive outputs, or do you want combinations to be valid? Epoch 88, 11 more, and we're done. So Harvey says, noted, thanks. You're welcome. All right, so I've been talking for about an hour now, so not bad. I'm nicely on schedule. So 10 more epochs and then we're done. And then I'll show you the chart, the plot at the end. And the plot is going to show the accuracy of the final neural network. So how good is it at recognizing dogs and cats? So our testing error is now at 0.212. So it's not bad. Maybe we can get it to below 0.2 if we're lucky. 209. So keep your fingers crossed. 6 more epochs to go. It's really cool, actually, that I can train a neural network and run this Zoom session at the same time. My computer can actually do that. Bob, in a business application, these tools can be used to determine who are the best customers, best region for sales, if sales are dependent on time of year, if temperature fluctuation affects sales, etc. Exactly. Yep, that is completely correct. So you can use these neural networks to discover all kinds of cool patterns in your business data. Okay, the last epoch, here we go. Ah, 204. So, okay, so look at this. So the final test error is 0.2, and the final test accuracy is 0.8. Remember, accuracy is 1 minus the error. So we have an accuracy of 80%, 80% or 0.8. So this means when I show the neural network 100 images of dogs and cats, 100 images of dogs and cats, it will correctly identify 80 images, and it will make mistakes on 20 images. So 80% accuracy. That's pretty awesome, actually, isn't it? So a simple neural network, it only had like, what, 10 layers or so? I just hacked it together in 118 lines of C# code. I was training it for like 10 minutes, and I have 80% accuracy. Really, really cool. You can get this higher. You can get all the way up to 96% accuracy, which gets really close to human level performance. Human level performance is somewhere in the range of 98%. So the neural network is really brushing against human level performance here. And the way to do that is just add more layers. If you want human level performance, you need about 18 layers, 20 layers, something like that. You need to have about 20 neural network layers. And then you get human level accuracy on recognizing cats and dogs. But this simple code example already scored 80% accuracy. So I think that's really cool. If we were to identify those 20 images that are incorrectly identified, you could probably recognize that it makes sense that the neural network struggles. If you look at some of the images, then I mean some of them are quite difficult to identify. Like for example, this one. Let's see if I can make it bigger. See, this one's kind of weird. It even has text in it, and a weird background. It's like right here. Let's see what this one looks like. See, the dog is a bit small here. Lots of grass, tiny dog. Look at this one. Not much contrast, right? I mean, the fur of the dog and the carpet, almost the same color. So not a lot of contrast for the neural network to work with. So these images are difficult. This is a hard problem to solve. And the fact that we got 80% with a simple neural network is pretty amazing. So the reason that this works is because the convolution layers are just awesome at recognizing visual patterns. Convolution is this fantastic process for building neural networks that can recognize stuff in images. Convolution was discovered it's a very old mathematical operation, but using it in neural networks, people only started doing that about 8 years ago. 8 years ago. So this is really modern technology, really modern stuff. We only have accurate visual neural networks for about 3 or 4 years. So having computers looking out in the world and recognizing what they see, that's only been possible for 3 or 4 years. So there's all kinds of cool software applications that you can build with this. Just realize computers can now see and they can understand what they are seeing, and just run with that. See what kind of cool applications you can design with that. Okay, let me switch back to this thing and go on further. So that's the end of the workshop. So are there any questions? Are there any questions on what you saw today about neural networks, about C#, about CNTK, about building, seeing computers that can, you can hook them up to cameras, and you can point the camera outside, and the computer knows, like, oh, there's people walking around, all kinds of scary stuff that you can think of, you can do with a neural network. Bob, what apps are CNTK not good for? Text analysis. So analyzing English text and determining the meaning of text and generating text from scratch, or asking the computer a question and getting a coherent answer. So extrapolating, from a question what the intent is, and then generating English text as a response. So text generation, CNTK is not good for that, because you need a very specific neural network architecture for that, called a transformer, and they are not implemented in CNTK. Abhishek, can the matrix multiplication convert it to addition by taking logarithm and then take the anti-log for the final output? That's a good question. I have no idea. I'm sure there are all kinds of optimizations built into the GPU, but what those are, I have no idea. For me, that's the hardware level, that runs the algorithms, and yeah, that's as far as my knowledge goes on that. So my answer to that would be probably. Any other questions? Can you think of applications for neural networks? You guys have any plans to implement neural networks for personal fun, or? I can give you a couple of examples of apps that I've built with this technology. I built face recognition systems, so where I would hook up my computer to a camera, and then the computer would just track my face, like that, and it would recognize me on camera. Can point the camera outside, and film a crowd of people, and then count all the unique people in the image. So you do face recognition, or face identification, basically, and then look at all the unique faces that are on camera. So you can basically count people. You can film a crowd, and you can say, okay, that's 246 people, and you can track individual people as they move around. So you could use that for security software, like on an airport, you can track the movement of people. This stuff is actually being used in shops for theft prevention, by tracking how people walk through a shop, through a supermarket. It turns out that people who steal from shops have a very specific way of walking through the shop, because they're avoiding the cameras, they're avoiding the security guard, so they have a very convoluted way of walking through the store. And the computer can recognize that path, that walking path, and then so it can identify possible thieves. I built an app that recognizes celebrities, so you could actually point the camera at yourself, and it would tell you if you are a celebrity or not. So I filmed myself, and the computer said you are not a celebrity, unfortunately. I made an app that you can point the camera outside, and it will describe what it sees. So, I'm outside on the street, and I'm filming, the street, and the computer will then could generate a description, and it will say, okay, so you're standing on the road, and I see cars, and I see bicycles, and there's a shop in front of you, stuff like that. You can do that. So you can build all kinds of amazing stuff. This is really powerful stuff. Abhishek, is the CNTK good for NLP or sentiment analysis in sentences? So what I just told Bob, it's not good for NLP, so it's not good for text analysis, but you can definitely do sentiment analysis. You can do sentiment analysis where the ordering of words is unimportant. So when you create a sparse vector from your input text, and basically you just put all the words in a long vector, and you present that to a neural network, then you can do fairly accurate sentiment analysis on that. You would use a one-dimensional convolutional neural network for that, or a recurrent neural network, an LSTM network. And they are pretty good at sentiment analysis. However, if you want to do super accurate sentiment analysis and look at the specific ordering of words in an English sentence, then you need a transformer neural network. And you can only build those in Python for now, in TensorFlow. But I have an assignment, I have an exercise in my course, which is sentiment analysis. I've got a database with a couple thousand messages, and you have to identify the spam messages. And I have a database of movie reviews, and you have to identify the positive and the negative movie reviews. So that's binary classification on text. And we use neural networks for that. So that works fine. Bob, intelligent retail operations to track best location for displaying products. Yes, you can do that by tracking where products are placed in a shop and then calculating the corresponding revenue. So if I put my cornflakes here, you put your cornflakes in a certain location, and then you calculate how much cornflakes revenue you get over a period of a month. And then you try a different location, and then you calculate, and then a different location, and then you calculate. So you build this huge data set with products by location, by revenue, and you feed that into a neural network, and then you simply ask the neural network, I want the highest possible revenue, give me the location. And the neural network will tell you the location where to put the products. So you can definitely optimize it that way. There will be a pattern, cornflakes need to go somewhere, to get maximum sales. Cornflakes probably have to go low on the lower shelves so that kids can grab them, And kids can grab them and go, Mommy, I want to buy this, buy this for me. So the neural network will learn those patterns by looking at your data set. The big challenge will be to generate that data set. But once you have the data already, training a neural network on that is trivial. You can definitely do that. This is cool. I like this brainstorm. Any more ideas? What was a cool idea for using a neural network in business? Abhishek. Do we have any coding assignments as part of the session? No, you don't. This was just a demo of the code. If you want the coding assignments, you have to go to the course because it took me a lot of work to create these coding assignments. I've been working like 2 or 3 months non-stop on this course. So I'd like to get paid if you don't mind, So no coding assignments, but check out the course next Monday. And it has how many coding assignments? Like 10 or 15, I think. Real world data sets. So data from the real world, from businesses. We have sentiment analysis, text for sentiment analysis. We have service data. I've got a taxi fare database where you have to calculate the taxi fare for a New York taxi company, predicting house prices. I've got images. This dog and cat exercise is in the course. So you will build this neural network and then you will take it all the way to an accuracy of 96%. So that's in there as well. All the assignments are in the course. Okay, Bruce, the lack of a GPU or a well-powered Windows PC may postpone my enrollment of the second course, but eventually I will enroll. Okay, so Bruce, keep in mind, I created the course with a MacBook Pro without a GPU. So, and that works fine. I mean, what you just saw, this exercise, it will run on your computer. It will just take 2 hours to complete instead of the, 10 minutes that you just saw. So if you are willing to wait longer to run and train your neural networks, then you can definitely do the course with your computer. Almost all assignments will run on your non-GPU computer. So please don't let that stop you. So Bob, thank you. Thank you, Mark. Always interesting. Bob, thanks for showing up. Always a pleasure having you in my workshops. Abhishek, thanks. Thanks for coming. Okay, guys, let's wrap this up then. This has been 1 hour and 20 minutes. So Abhishek, Bruce, Dom, Harvey, Jeremy, Joan, Murali, Prasant, and Seri, and Mark, that's me. Okay, so that's everyone. Thank you for watching. Thanks everyone. I hope you enjoyed this. I hope you realize all the cool stuff you can do with CNTK and C#, and that machine learning is now available to us C# developers. There are no limits You can really get started with AI and have some serious fun building cool applications. Yeah, check out the course. And if you like what you see, please consider joining the course. I would love to see you in the course and walk you through all these cool assignments and help you build awesome neural networks on your own computer. Okay, thanks everyone.